Okay, welcome everybody to the 10th session. So this is the second session of the series on column, on HPLC column, which is the heart of any HPLC system. It provides retention for your analytes and hopefully differential retention, meaning that you have separate retention time, right? This is really important for UV detection for quality control. Okay, there's a second one. Last one we talk about column dimension. Now, even though it's very mundane, it's very ordinary, people don't pay attention to dimension. Dimension, the length of the column and the inner diameter are really, really important on the operation, right? So people might not pay attention to it. And I hope that you can appreciate the somewhat complexity and how the intermingling, the intertwining factor affect your chromatography, operation, separation, things like that. Now, particularly it's important under gradient condition. Under gradient, you really should use a higher flow rate. Okay, agenda for today is on a focus on bonding phases and bonding chemistries, and also on the Van Deemter's plot, right? Van Deemter's plot is the most important equations. And we're going to explain that a little bit deeper. I'll tell you the story of Van Deemter. Why do we call it play count, right? So for today, we talk about different types of bonding phases. And once again, we focus on reverse phase, right? Reverse phase is going to be our focus. And then there's also normal phase, bonding phases, ion exchange, and the different selectivity differences between different phases, right? So we'll give you a little bit of what that means. Okay, so we're going to introduce to you the traditional bonding phase chemistry, what we call the monofunctional silane, using a silane as a ligand, as a attachment, with only one functionality, one chloride, one chlorine atom to attach it to a single point, right? A lot of the newer column actually are called using trifunctional silane. Trifunctional silane means that the monomer of the ligand have 3 attachment points. And ideally, it would attach to the silica with 3 different points, right? That's ideally. In reality, it might not happen, right? You don't really know how it get attached. Sometimes it get polymerized. So monofunctional silane are very reproducible, right? Which is a great thing. So there's always some pros and cons. There's something called end capping. So after the bonding with the big ligand, you use a small silane to end cap it. So all columns, with very few exceptions, are end capped to keep the silica surface inactive, right? You don't want it to be too active. You want the primary retention mechanism to be hydrophobic interaction, right? Meaning partitioning or dispersive forces, very weak forces. Recalling high school chemistry 101, we talk about different bonding chemistry, and we say the ionic bonds are very strong. We talk about dispersive forces, such as the forces between the rare gases. Okay, so sometimes when you talk about argons, they kind of come together by dispersive forces, right? So these are very weak forces. Also, residual cyanols are really important. That's kind of the problem sometimes we have when one column from different batches of silica is not reproducible. It's the #1 complaint 20 years ago. But today, we have solved the problem overall. And that's by the introduction and the need for using high purity silica, right? So that problem was actually solved by Dr. Jack Kirkland, right? He's really a bright guy. And he actually is the guy who invented SPP, or superficially porous particles, without actually doing the experiment. You know, he's a physical chemist, so he actually is had very high impact. I'm a big fan of Lloyd Snyder and also Jack Kirkland. And then finally, we talk about Van Deemter equation, this chemical engineer from the Netherlands, and how he actually make a deep impact into the chromatographic theory. So explain to you the A term, B term, and the C term. And also the ramification, right? What does it mean to you? What does the A, B, C term mean to everybody working in the lab? And also, how do we estimate the plate counts from the column length and the particle size? So you can actually make an estimation, rough estimation of the plate count, right? It might not be exact, right? But you can just guess, estimate what it is by just knowing the length and the particle size, right? So it would be actually pretty accurate. You can also measure it, okay? And when you measure it and you get the efficiency plate count, right? There's a many way to measure it, right? You can use the USP method. You can use 4 sigma base width. It all depends on the base width in relationship to the retention time, right? And you must measure the plate count under isocratic condition. I continue to see a lot of people reporting from the contract lab plate counts under grading condition. And immediately I would tell them that it's not correct. It's just wrong. You cannot measure plate count under grading condition, right? You can say apparent plate count, but that has no meaning. For comparing separation power under gradient, you would have to use something called peak capacity. So plate count is a no-no unless you measure it isocratically. So it's a very common mistake, right? So next time you see other people are reporting plate count under grading condition, please yell at them, say that you're wrong, okay? Okay, so common bonding chemistry, right? So here's a listing of the common bond. It's come from chapter 3 of the book. Okay, so once again, C18 is the most dominant bond phase chemistry. I would say more than 50% of the column, the methods I've seen are using C18 column, even though you have thousands of different bond phase to choose from, right? It turned out that this is the most dominant, and actually it works really well. Now, the reason why it works well because it's very hydrophobic, it's very reproducible. It works for almost everything, right? So why not using C18, right? So I think C18 is the one you should use to start your method development. Most likely, a lot of methods using TFA, right? TFA actually is not ideal, but it works so well and good enough for most applications. It's actually not very mass spec compatible, unfortunately. You can use TFA for single quad, but never use it on ion trap. On some of the high resolution mass spec, right? They're really a lot of people like octyl. Okay, so some of the practitioners actually like C8 versus C18. I actually prefer C18. The reason why C8 they think is better is because it's a little bit less hydrophobic, but definitely I think C18 is much more reproducible, right? So why not use something stronger? Cyano actually is not very useful, right? There are people that do not believe cyano actually is a good stationary phase. It gives you different selectivity, but you can get the same kind of selectivity from switching methanol to acetonitrile because it's the same cyano interaction. I like phenol. I think phenol is really good for pharmaceutical analysis. Why? Because most pharmaceutics have a aromatic ring, right? So with phenol, you give a little bit of selectivity for those group with aromatic ring, right? So sometime when C18 does not work, right? Well, you always start with C18 in the method development. When it does not work, go to a phenol or go to a polar embedded. Okay, we talk about what is a polar embedded. A polar embedded is a bond phase where you have a long chain stationary phase giving you hydrophobic interaction. But in the middle of the chain, not at the end, in the middle of the chain, right in the middle, you have a polar group. You have either an amide group or a carbamate group. So for Waters Corporation, which is probably the top column manufacturer, they use the carbamate chemistry. For a lot of other people, they use amide group, such as Agilent and also Supelco, Millipore, or I don't know what they are, or Merck AKAA, right? So A normal phase silica, which is not very good, right? It's too active. So a lot of time you actually put a bonded phase. I would say the normal phase bonded phase is amino, which is usually with a propyl linker, right? So you bond an amine to silica with a propyl linker to make it a little bit hydrophobicity, a linker, right? You can have a hexyl linker, a C6 or C3 linker. Okay, ion exchange is a different category altogether, right? So you use that for ion chromatography. I use quite a bit of that for biopharmaceutical. If you want to QC a monoclonal antibody, one of the fundamental purity assay is ion exchange, right? I use a strong ion or weak ion exchange, right? And you can have two category, either anion or cation exchange, right? So these are the ion exchange bonded phase. Okay, so here is traditional bonding chemistry, and I show you both the ligand or the bonded phase, and also the end capping agent, right? So here I have the silica surface. Now, what is silica? Silica is SiO2. It's actually sand, right? Sand is silica, right? I mean, you can basically pack sand into a column. The problem with sand is that it's not porous, right? So in order to have a high surface area to do all the bonding, to do all the interaction, you need a porous silica, right? So in the early days of liquid chromatography, we take sand and we actually treat them and make it porous and make it round or into something which we can sieve it. Sometimes we sift it to give you a different particle. And those silica are irregular. They're not the best chromatographic media. Later on, we get better and better, right? Now they are becoming very expensive. They also are much better. Okay, the traditional silane chemistry is monochlorosilane. So this is called a monofunctional silane chemistry, where you have let's say diether. This is the Ca group, right? You have a Ca chain, and then this is the ligand that you bond to it before it bonding, right? You have a single chlorine atom, which is a leaving group. And then you do an organic reaction, right? Reflux it using a condensation reaction, and you get rid of the HCl, right? So at the end of it, Ca dimethyl silane get bonded to the silica surface, right? So you have one anchoring point, right? Rather than two or three. Now, unfortunately, it's not possible to bond 100%. That's the problem. Why? Because these are a pretty big group, right? It's kind of very hydrophobic. It's a large group, particularly with the C18 group, right? Imagine most of the silicas, residual silanol group, are within the pores, right? So no matter how long you cook it, it's not possible to get 100% bonding. The best you can do is about 50% bonding, right? So it leaves a lot of residual silanol group on the surface, and those are really bad. Could be really bad, right? Unless you do the right thing. So the next thing we would do end capping reagent, right? We'll put a small silane, right, such as trimethylsilane in there. So these are smaller, is able to go inside and perhaps bond to it with a condensation reaction, just like the bonding chemistry with monoclonal silane, right? So with HCl being boiled off, and then you can bond that. Once again, you cannot get 100% bonding, right? You leave a lot of residual silanol group. So almost every column, most column are end cap, right? Okay, so here is a figure, courtesy from Waters Corporation, to show them their bonding chemistry, right? So everybody using the same thing, right? You have silica, which is in a network, right? And then after bonding, you have residual silanol. Now, residual silanol could be, it's a problem. Why is it a problem? Because they could be acidic, right? I mean, you can see the OH group, right? There's somewhat acidic. And you do not want acid-base interaction, because that is much stronger. And that's the result That's the reason why you have peak tailing for any basic drugs, right? And in some of the packing material, particularly in the old days, they are so strong that if you inject caffeine, it would never come out unless you use a masking agent, because the silyl group are so acidic. They actually bound the caffeine to it, unless you use a masking agent such as triethylamine to deactivate the column, the residual silyl group. It would never come out, right? Okay, there are different types of silyl groups on the surface of silyl, right? So you have associated silyl group, and they are not bad because with association, they are weak. So they are not very acidic. You have germinal silyl group, which is more acidic. A free silyl group are more acidic, right? But the worst case scenario are the one which is adjacent to a metallic oxide. Now, in the old day, there are plenty of metallic oxide because we get our silica from sand. We get it from the mine, and we treat it with acid and make it porous, and then sift them into a regular size, and we pack them in the column. So the silica with a lot of metallic oxide become very strong, and they use that all the time. But they are not good for anything basic because you have acid-base interaction. Okay, so this is really what makes things really bad and not very reproducible. I did that in the 1980s when I worked for PerkinElmer, right? So we compared two columns. One is called HPLC BDS C18, made by the HPLC Corporation in England, right? So this was a very popular silica support in England. And the other one is water symmetry C18, right? You can see that I injected 5 compounds, a mixture, and 2 of them are basic, pyridine and dimethyl and dimethyl aniline are basic, right? The other one are neutral, right? You can see that both columns give very good play counts for the neutral compound, right? We are just doing a methanol water without any ionic additive, without any acidity, basically. We didn't adjust anything, right? So this is what happened, right? So the question is, guess which one have more metal in the bulk silica? And the answer obviously is HPLC BDS C18, right? Because the metallic oxide activate the residual silyl group and actually make it into, because of resonates with the b orbitals, with the empty the d orbitals in the metal orbitals, it become ionized and become O -1, right? Which become ionic interaction with anything that's basic, right? So that is really bad, right? You can see the tailing is just not acceptable, right? Okay, so here I want to describe novel bonding chemistries. What has happened. It's very important to have more efficient bonding, right? To have higher coverage. So traditionally we use monofunctional silane, and the best we can do is about 50% bonding efficiency, or about 2 micromole per meter square. There are more and more companies using polyfunctional silane, difunctional and trifunctional silane. I would say a difunctional silane within a dichloro is kind of not common today, right? I think the first Sunfire from water was using difunctional silane. The first Atlantis column is called D2, and they found out that it's not very reproducible. Every time you make it more complex, it's less reproducible. And trifunctional silane are actually much more popular. It seemed to give it a more high pH range, right? So those are used in Acuity C18, right, in water's HPLC column. They're using trifunctional silane. I still think that the monofunctional silane are much more reproducible, such as the one used in ACE column. But more and more manufacturers using trifunctional silane. I'm a big fan of the phenyl column and also PFP. So phenyl boniface have pi-pi interaction, quite useful in pharmaceutical analysis. And PFP actually give you a mixed mode interaction, particularly for very polar drugs and polar compound. There's a class called polar embedded group, which I'm a big fan of, particularly useful for resolving complex pharmaceutical analysis because it's using a mixed mode interaction. Now, what do I mean by mixed mode interaction? Later on, we can talk about charge surface hybrid. I think that in 2 weeks we can talk about that. So right now, I'm not discussing that. So C18 and CA, mostly hydrophobic interaction. Phenyl, pi-pi interaction. PFP, your pi-pi dipole-dipole moment, also your hydrogen bonding. Because you have a very electronegative fluorine atom, right, which is a prime example for hydrogen bonding. Polar embedded actually is a mixed mode. You have hydrophobic interaction, dipole interaction, and also hydrogen bonding. So 3 different modes in the, unfortunately, every time you have mixing more complex, like a polar embedded column, the chemistry is much more complex. The reproducibility is a little bit less, right? It's not as reproducible from batch to batch, right? So if you can do with the monofunctional silane C18 chemistry, I would prefer to do that, right? But a lot of time for very complex drug substance separation, you cannot do it. So you always rely on some little bit different selectivity, meaning using pi-pi interaction with the phenyl column, or a polar embedded column using an amide or carbamate chemistry. Okay, so once again, a novel bonding chemistry, right? So first one is Solbeck stable bond, right? Now this is the innovation from Jack Kirkland again, right? So Jack Kirkland think that in order to have less problem from residual silyl group, so instead of using a methyl monofunctional silane with a methyl group on that, he actually used a bigger group using an isopropyl group, right? So idea behind it is to shield it, okay, so that the residual silyl group is being shielded, being protected, right? So there are many ways to kind of deactivate the silyl group, right? So this is one way. The other way is to put some type of polymer on top of it. They would not tell you how they do it, right? So most column manufacturer, they keep them proprietary. They would not patent it. They might patent it, but they would not disclose the process, right? So it's called sterically protected. It's called stable bond. There's no end capping. Okay, so anything stable bond has no end capping. Stable bonds are trademark. Okay, so the first sign of a difunctional silane was in 1990s. Using Waters Xterra. I think this is 1999. So this chemistry is called difunctional silane chemistry. They're using dichlorosilane. So ideally, in this cartoon or picture, you have 2 attachment points. In reality, you actually might have polymerization. Every time you mix, you have more than 1 bond in the ligand. It can cross-link and do all kinds of things. Same thing with trifunctional silane. But difunctional silane is definitely our favor. Very few people are using it. I think Waters probably discontinued the D2 chemistry. They used to call the Atlantis column D2. Now it's T3, trifunctional silane. Also, embedded polar group or polar embedded group, such as Waters Xterra LP8. So in a octyl chain, they have a carbamate group in the middle, embedded in the middle, right? So this one actually was able to do a little shielding of any residual silyl group, right? Okay, so here in this chromatogram, I want to compare a family of Waters columns, right? In Waters column, here's the family, right? They have all these kind of strange names, right? So CSH stands for charge surface hybrid. We will cover that later. HSS stands for high strength silica, right? T3 stands for trifunctional silane. Okay, so this is, but by using T3, you can kind of decipher what it means. SB, I think, is stable bond. Okay, so I think SB is a stable bond, very similar chemistry as the Sorbax. Okay, so you can see that when you inject 7 different drugs, you have different selectivity, right? So some of them are very similar. For instance, the hexylphenol are quite similar than the C18, but something like pentafluorophenol are very different. You can see 1, 2, 3, 4, 5, 6, 7. Okay. Cyanol is very similar. PFP, pentafluorophenol is also very different, right? This one looks a little better, okay, than the CSH. This is T3. You can see very similar. So most C18 are very similar, but they do have small differences. So most C18, there are thousands of C18 columns, right? So if you have just one peak, right, using a C18 column, then it doesn't matter. You can use all kinds of C18, it will work for you. However, if you have a very complex separation, then you actually have to specify the part number for the C18, right? So they are not the same, right? There are differences in bonding density, residual cyanide activity, and things like that, right? So all C18 are not the same. So definitely you have to specify the part number of the column in order for it to be reproducible. You're also relying on the manufacturer to keep everything well quality control so that anybody can reproduce your separation by buying another new column with the same part number, right? In the old days, it's also kind of a problem, right? Because you develop a good method, right? And then you transfer it to QC, and then you get a phone call and say, hey, Michael, you screw up because I cannot reproduce your separation. They are using the same condition, same column, right? But the column is from a different batch of silica, right? If you don't have good quality control on the silica material, the silica is not well made, then you don't have good reproducibility, which is required in QC. Okay, here's an application from Bristol Myers Squibb. Okay, so how do they do this column? Now, this is a drug product with 2 API, right? So a little bit more complex, right? And you can see the C18 does not work, and they have to use phenyl-hexyl. I'm pretty sure they start with the C18, right? When they do not get selectivity between the different resolution test mix, they have to go to a phenyl column, right? So they are lucky. And they use something very simple mobile phase, right? 0.1% TFA. And so this is very simple mobile phase. Yeah. Okay, here I want to show you one of my study. Okay, I do a column screening. Okay, so this actually is a real one in my project. Okay, I'm trying to develop a method for a new drug candidate or a new chemical entity, right? And I did a force degradation, right? I shine light on it and it got degraded, right? And I want to make sure that I have the best column that can separate out the impurity, which is called aniline analog, and also 2 degradation product, which is A and B, right? Now, but I'm having some trouble with C18 column, right? Because the peak looks kind of broad. So there seems to be something underneath the API peak. So I do a column screening. I use a very small column, a sub 2 micron column. This is a very, very small column, right? And I can do a very quick screening in about 30 minutes, right? I can do a 10-minute full gradient. And when I do screening, I can see the power of the polar embedded C18 column. You can see that I should pick this column because it actually separate out 4 peaks, right? So in method development, you're always looking for a method or condition that allow you to have more peaks, more separation, right? Because something like that, even though it looks very pretty, is bad, right? Because 2 of the pairs are co-eluding, right? It looks actually perfect, right? So without comparing it, you don't know, right? So this is a kind of a little tricky separation here. So right away, we know polar embedded is better, and I will use a longer polar embedded column from the same manufacturer to develop the method. Okay, so UHPLC, expedite method development. Okay, so definitely if you have a UHPLC system coupled with UHPLC column, it is really good. Make yourself much more powerful and efficient. particularly with a mass spec attached to the system. You can do a lot of column screening very, very quickly, because using a short column like this, you can analyze things basically in 2 minutes, 3 minutes, or 10 minutes. I think 10 minutes can give you a lot of separation power, right? Rather than using a long column. Okay, I want to talk about something which you may or may not have experienced, called phase collapse. The better term is called pore de-wetting phenomena, right? And what is it? Okay, one of the problem or limitation of C18 column, even though it's great, was the inability to retain very polar compound. If a drug is very soluble, water soluble, you have no retention in C18. It does not want to go inside and interact with the C18 because it's very polar, such as uracil, right? It's kind of a void marker. Okay, so how do you do it? Okay, you keep lowering the solvent strength, right? So you go from 100% all the way down to 5%, and still is eluding with the solvent front, right? So what do? You can go down to 2%. And then, wow, okay, you get a little bit of retention, right? It separates away from your solvent front, right? Which is great. Okay, and then, okay, so you have a method, right? A 2% methanol, 5% methanol, whatever it is, or 10% methanol, a very low solvent strength, right? And then you go to lunch, right? When you go to lunch, you decided to be a very green, environmentally friendly. You turn off the pump, right? Once you turn off the pump, then bad things happen, right? When you come back and you inject your sample, right, you have no retention. And suddenly, it's like the column is no longer reproducible. It's a phenomenon called a phase collapse, right? So people think that maybe what happens that when you use a high level of acetonitrile, the C18 phases, which are very hydrophobic, like brushes, they were kind of waving around, right? And then when you were using 5% methanol acetonitrile, and then you stop the pump, right? So the phase collapse and stick with each other, right? So you have no C18, which are, so this is what people think is called phase collapse. The better terminology is called pore de-wetting, right? Actually, Fabrice Greedy, who actually, he's a very excellent theoretical chromatographer. He published a lot of paper. I'm a big fan of Fabrice, right? So most of the C18 are inside the pores, right? So when you use a lot of high concentrated acetonitrile, all the pores get wetted, right? Now something about water have very high surface tension, right? You know, when you have a drop of water, it comes together as a bead, right? Because of high water tension. Okay, once you stop the pump, right? The C18 kind of expel the any solvent from the pore, right? So you have a situation, and no matter once it gets expelled, you cannot pump, and you try to pump that again, it will not work, right? So you have to go back to 100% acetonitrile for it to be able to enter the pores, right? So it's called a phenomenon of pore de-wetting, right? Now there's a fix for that, right? So Waters 20 years ago, they actually make a column called Atlantis, right? Now they were using a difunctional silane group. Okay, now this column is obsolete, right? They no longer use a DC18. They use a T3 Atlantis column using trifunctional silane, right? So I know that difunctional silane is not as reproducible as trifunctional silane. So what happened here, right? So you can see that they were doing this mobile phase, which is using 100% aqueous without any organic in order to retain some of these very polar compound, right? And a regular column, you can see aniline number 1 is not retained, right? Atlantis, however, is away from the solvent, right? Have some retention. Now, how do they do that? They won't tell me. I keep asking them how does the bonding chemistry well. And finally, I get some inkling, right? It's number 1, they are not fully bonded, meaning that they are not pushing the, they're not, the ligand density is very low, right? Meaning that they don't they do a partial bonding, which sound kind of very bad, right? But it's not fully bonded, right? And they're not end cap at all, right? However, the silica is also good silica. It's actually very using high purity silica, right? So silica is actually very good with very low metallic content, right? So they have low solenophile activity. So meaning that their peak shape for basic compound is not too bad, right? So this is for polar analyte, right? So I actually use this column for several of my drug development project using a drug which is highly water soluble. Okay, let's go to Van Deemter curve, right? Van Deemter, now anybody with a last name of Van most likely came from the Netherlands, right? It's a Dutch person. Van Deemter is a Dutch chemical engineer. Most chemical engineer actually work with petrochemical, right? So they're very familiar with the process of doing distillation of the crude oil. Now here is a big column. It's called a column. They're at least 5 stories high, and they have different plates inside the column, different plates. These are bubble plates. You put crude oil in the bottom, you heat them up, and then at the outlet you have methane, which you burn them, okay? And you make naphthas, gasoline, at least 30% are gasoline, kerosene, diesel, lubricant, heavy fuel oil, right? Number 2 heating oil, number 6 heating oil. At the and the bottom is your bitumen and asphalt, right? You use it for paving roads, right? So this is the distillation process. The more place you have, the more fractionation, the more separation you get on the crude oil separation, right? Okay, so here is the Van Deemter curve, right? So Dr. Van Deemter published a very important paper in 1956, right, in chemical engineering science, and he spelled out the plate theory in chromatography, mostly actually for gas chromatography at that time, but it actually works well for liquid chromatography. He would say that the efficiency of the separation can be expressed as a number of plates, right? And the plate actually is defined as a plate height, right? So in order to have many plates, you want to have a plate height which is small, right? So the smaller, the better. Okay, so the height equivalent of a theoretical plate, or H is called the plate height, is equal to the length of the column divided by the number of plates, right? A number of plates measured by the equation I showed before, right? In the theory part, using a ratio of the retention time over the peak width, right? Is to the square function and times 16 or whatever equation that you use, right? Okay, so the plate height actually is expressed as 3 terms. It's called the 3 Van Deemter terms, so A, B, and C, and they have different ramification and derivation, right? And they behave differently, and they're related to linear flow velocity. The linear flow velocity actually is very similar to flow rate, which is volumetric, right? Except that the flow rate is depending on column in the diameter, right? Linear flow velocity is much more absolute terms, right? Okay, so the overall Van Deemter curve looked like that, right? Looked like a dip, right? Looked like a plow or a dip, something in the middle, right? And this is the optimum velocity. This is the best flow rate, and happening at the minimum plate height, right? Okay, and the overall Van Deemter curve is controlled by 3 factors, right? A, B, and C, right? A term is called the multipath factor, right? So it does not change with velocity. B term is called the longitudinal diffusion factor, which is like that, going down with high velocity. And C term is called the resistance to mass transfer, okay? So the 3 different factors. Okay, so to refine it a little bit, you can see that this is the Van Deemter curve, right? You can see they have H is equal to the A term. B term is related to the diffusion coefficient of the analyte, okay? And also U is the linear velocity. And C term actually is actually proportional to particle size square divided by the diffusion coefficient of the analyte, right? You can see that over here. And also related to the linear velocity, right? So it's A, B, and C term. Okay, I'd like to kind of give you some meaning behind that. What is A term, right? Explain it kind of intuitive way. A term is called the eddy diffusion term, right? So it's how well the column are packed, right? In order to have good A term, the particle have to be similar size and have to be well packed. If you have a big hole in the packing, if you don't pack it well, it's loosely packed, then the A term would overwhelm it. You have no column efficiency, right? You want the particle to be evenly distributed and very, very tightly packed, right? There's not a lot of throughput, right? Now, why is that? Because if you have 1 microliter caffeine solution, you have billions and trillions of molecules, right? They go down the column through a random walk, right? Now, every time they hit a particle, they would go through the interparticular volume of the column, and they actually would diffuse inside to the pores, right? And they have to diffuse out, right? So there are billions of interaction, except you don't care about it. It happened automatically without you worrying about it, right? And billions of these molecules, trillion molecules, behave the same because they have the same physical chemical property, because they have the same equilibrium constant, right? So if you're caffeine, or if you're theobromine or something different, you would behave different and you would wind up with different retention time, right? Okay, so this is the A term. Now, B term is longitudinal diffusion, right? Now, you think that if you use a very low flow rate, you have better separation, right? But that's not true, because if your flow rate is too slow, then every time the band of your analyte, which are separated, are traveling outside the particle, right? Once it, swimming in the mobile phase, they are very concentrated, right? So you have natural diffusion from high concentration to low concentration, right? So if your flow rate is too low, the natural diffusion would kill you, right? Meaning that you spend all the money to separate into a sharp peak. If you left the band to be in the column for too long, you have natural diffusion going against you, right? So you don't want to use a flow rate which are too slow. Now, you don't want it to be too fast either. It's too fast. What happened? You have something called mass transfer. Now, what is mass transfer? Most of the problem with mass transfer is what happened when the analyte go inside a pore, right? Because the mobile phase inside the pore are not moving, they're stagnant, right? They're not moving. So if they go inside a pore, they're not moving at all, right? So you're allowing the interaction. Eventually, you want the analyte to come out, diffuse out of the pore, right? And that takes time, right? And once it goes to a pore, it would travel with the mobile phase, right? Until it hit the next particle and go inside the pore, right? So it's definitely a very complex thing, right? So very important to use small particle size because the pores are not as deep, right? The mass transfer are better, right? So you have disconnect between the profile of the analyte in the mobile phase, traveling with the mobile phase velocity, and the one that kind of the concentration profile of them interacting with the C18 material, right? And most of these are inside the pore, right? So the stagnant pore of the mobile phase inside the pore is really mostly responsible for the mass transfer C term. Now, what does it mean, right? So this Van Deemter curve came from Najin Wu of Cell Gene. So you can see that with 5 micron packing materials, the minimum plate height is about 10 micron, right? So typically the A term, which represent the minimum plate height, is about the 2 particle size, 2 times the particle size, right? So so right away you know how to calculate n, right? Because from the column length, from the particle size, you can calculate n. If you have 1.7 micron, which is sub 2 micron HPLC acuity column, for instance, right? The minimum plate height actually is twice of that of 1.7. So 3.5 is the plate height. You can see that the minimum plate height is that. Also, the minimum the optimum velocity of the minimum plate height also gets shifted to higher velocity, right? So that's why you use small particle to give you fast separation, right? Because you have much lower C term, right? C term is the mass transfer term, right? They're flat, meaning that you can go to very high flow rate with very loss of column efficiency, right? Yeah, so that's what I mean, right? While 5 micron, which is 3 times smaller, the slope is 9 times higher, right? 10 microns even worse, right? It's like this, go up like that, right? Okay, so those are the Van Deemter curve and the ramification. C term is proportional to dp squared, and the optimum flow rate shift to higher velocity or higher flow rate for smaller particle. Now, how do you estimate n, right? So very easy. The H minimum is the A term, which is 2 times the particle size. N is equal to the length of the column divided by the plate height. So if you have a 5 micron column, 15 centimeters long column, you get 15,000 plate. For 1.7 micron column, you also have 15,000 plate, right? But you can see that your analysis time is much faster, right? Because the column length is only 5 centimeters. It gives you much faster with high resolution. The problem is the pressure drop, right? The pressure drop between 5 and 3 are 9 times higher pressure if you want to use the same flow rate. So summary and conclusion, traditional bonding chemistry using a monofunctional silane, residual cyanol are reduced using end-capping procedure using trimethyl monochlorosilane. Any metallic oxide can activate residual cyanol group, causing a problem with peak tailing for basic analyze. A novel bonding chemistry, besides C18 bond phase, other useful bonding chemistry, in my view, are phenol, PFP, pentafluorophenol, and polar embedded phases using amide chemistry or carbamate chemistry. So Van Deemter equation is the equation describing how plate height changes with flow rate or linear velocity. There are 3 terms, right? The A term is eddy diffusion, B term is longitudinal diffusion, and the C term resistance to mass transfer. So here are the references.